today we have Haggai Lupesco. Haggai has been building software for the past 15 years in various domains, 3D medical imaging, global web-scale systems, and deep learning systems used at scale by engineers and scientists worldwide. Yeah, today Haggai will be talking about recommendation systems at Facebook. And please, if you'd like to kind of introduce yourself further.
Hi, everyone. Thank you for the introduction. My name is Haggai Lupesco, and I'm going to talk to you today about recommendation systems with deep learning using PyTorch. Let's actually get to it. So our agenda for today, we're going to talk about the business problem we're solving with recommendation systems. And then we'll talk about, we'll go through an overview, a brief overview to recommendation systems, how they're architected. We'll dive into exploring a deep learning model used within recommendation systems, and then we'll take a look into how we can optimize that model further and what's the approaches that can be taken in that regard. Looks like there's some comments that someone can't hear me. Can someone confirm whether they can hear me or not? Okay, thank you, Ravi. So it looks like the audio is working as expected. So let's move forward. So let's take a look at the business problem we're solving with recommender system. And really, it's a pretty basic problem that is relevant across many domains. And that problem is, what item will the user be interested in? And this is relevant across things like, e-commerce, what product to buy, other domains, what restaurant to go to for dinner, what song to listen to next, what movie to watch, what post to read, and the list goes on and on. Actually, recommendation systems are extremely prominent in requirement in the modern internet economy, and a very important problem to solve. And when you look at the business value achieved through effective implementation of recommendation systems, it goes through these three major pillars. The first one is engagement, and CNET estimates that 70% of the time watched on YouTube is actually driven by recommendation systems. That's a huge portion. When you look at customer retention, Netflix estimates that recommendation systems actually save them more than $1 billion per year in subscriber churn. And when you look at revenue, McKinsey estimated that 35% of the purchases on Amazon were the result of Amazon's recommendation systems. It's not surprising, but it just illustrates the importance and the business value of recommendations. Now, once we establish the business importance of these systems, let's take a look at how these systems are typically architected and designed. There are two major parts I'll look to here. One is the offline system, and the other one is online. But let's start with offline. It's typically called the ML pipeline. So the ML pipeline is a system with the objective to produce an up-to-date and accurate model that can be deployed to production. The system needs to evaluate, train and evaluate the model to ensure it meets certain criteria, and then publish it to production. Now, key metrics for such system is, first of all, of course, the offline model accuracy, and there are different metrics for that, like mean absolute error, root mean squared error, precision at k, recall at k, and there's others. It really depends on the specific model and the specific use case. The other type of metric are system metrics, especially around reliability, right? Because such a pipeline needs to operate, effectively and without errors as much as possible. So failure rate, mean time between failures, etc., are all important metrics. Now, typically, these offline ML pipeline has 5 major stages. It starts with data reading from the data store, reading of raw features and validating that these features are not corrupt. It then moves to the next stage, which is feature analysis and transform, with the goal of taking the raw features and converting them into features that the model can actually be trained on. Next step is model training and tuning, taking these raw features, feeding them to the model for training so the model can be trained to get to become accurate, and hyperparameters can be tuned, etc. The next step is actually evaluating the trained model to ensure it's not only accurate, but it also meets certain online or production criteria like memory usage, CPU usage, and other things. And lastly, once those criteria have been met, the model is published to production where it can take actual production traffic and drive the business metric. Now, the interesting thing here is that this process doesn't end. It goes back to the beginning and go through it again. Large-scale production models need to be retrained regularly because guess what? The data changes, the user changes, and also the model changes. So this needs to be working repeatedly. The next system is the online system, typically referred to as serving. And the objective here is to actually move the needle on the business metrics through recommendation to serve to the user potentially tens of items out of a much, much larger catalog, and do all of that within low latency. And of course, to log the user and the system activity for online evaluation and for offline training of the model back in the offline system we discussed earlier. Key metrics here are, of course, the business metrics, and those differ by the use case, but it can be engagement time with the service, retention rate, revenue or revenue proxies, etc. And then there's also system metrics around performance, like latency or memory usage, CPU usage, reliability, stuff like that. Typically, such a online serving system is composed of multiple stages. The first one is typically what's called a retrieval or candidate generation stage. And that stage, given the request coming from the client or the user with a relevant context, the goal of the retrieval stage is to fetch a set of candidates that are very likely to be a good fit. The focus here is less on precision, it's more on recall, just generating that list of candidates and doing it very quickly. And remember, usually the catalog has millions of items, and retrieval needs to retrieve, say, tens or hundreds of items. So that's the challenge there. Next, the set of items is fed into the ranking stage, which contains a usually higher complexity model that is able to do a much more accurate job at predicting the recommendation for each item. And that with that more accurate prediction, that result set is moved to what's typically a business rule stage, which applies different, usually hand-curated and programmed rules to ensure things like the diversity of the data set return, application of maybe user preferences, filtering out some things, enriching with some things. And then that result set goes back to the client device for rendering, for the user to see and engage with. Now, of course, all of this needs to be logged, what the user was presented with, what the user interacted with, because it's all get used later on back in the offline stage for model training. Now, in this talk, we'll actually zoom in to focus on the ranking stage. As I mentioned earlier, it handles the output of the retrieval stage and outputs a high accuracy prediction for each one of the usually tens or maybe hundreds of items before they're presented to the end user. This stage is usually less constrained in terms of complexity and latency. The focus there is actually having high precision, having accurate results. And as such, it can also take advantage of more advanced and complex modeling techniques, such as deep learning, which we'll look into now. So let's go on to look into exploring a deep learning model for ranking. So we'll need a concrete use case, and in this case, we'll take movie recommendations, something I think all of us should be familiar with, especially in these COVID times, where maybe we have more time in front of the screen, and not for work, but for fun. So the business problem is recommend a handful of movies to watch out of a large catalog in order to drive engagement, retention, and satisfaction. If we try to form the problem in more technical terms, we're talking about giving a user U and a movie M, predict the star rating, the user would give this movie had the user watched the movie, right? And that's usually in the scale of 1 to 5. That's the usual star rating scale. We could have picked also alternative definition of technical problems, such as predicting the probability of the user watching the video, or predicting whether the user will like the video. Those are all valid approaches, but let's stick with the star rating one. And of course, we need a data set. So in this example, we'll use the movie lens dataset created and maintained by Group Lens Research Group out of University of Minnesota. The link is in the deck. You can check it out, or Google to check it out. This group has been doing a fantastic job at curating this dataset and making it available to the community. Let's zoom in a bit into the movie lens dataset. So actually, there are multiple flavors. If you're familiar with this dataset, different sizes and different flavors to check out. We will use one that is targeting education. It's ML-latest, around 264 megabytes, so fairly, not a large dataset, but still large enough to be able to play around with it. It contains user rating with timestamps and user applied tags and movie genres. And when you look at the data set, there is 27 million examples, right, of users rating a movie. And that goes across 280,000 users and 58,000 movies. Interesting to note that sparsity, of course, is common in recommendation system problems. Sparsity is extremely high. So if you look at the user movies interaction matrix, 0.002 of that matrix only has actual ratings. The rest doesn't have any values. This is actually pretty common in recommendation system problems, and that's part of the challenge that we want to tackle. Let's actually do a quick exploration of the data set. It's very important to actually explore the data before you actually start modeling. So let me pull up this notebook. So this notebook, which is linked through the in the deck that you will have access to, as well as other notebooks we'll go through later in this talk. This one looks into the movie lens data set to do some basic exploration. We'll start by just loading the data. So there is a function here, load movie lens data set, that actually loads the data set and downloads it and loads it into a pandas data frame. You can see that it loaded 27.7 million ratings and 58,000 movies, like what we discussed earlier in the slide. Taking a closer look at the data, we can see that the rating table basically has rows with user ID, movie ID, rating, and timestamp columns. So we can see user ID rated the movie ID, gave it a specific rating at a given timestamp. There's 27 million samples like that. And the next table we have is the movies table that has a movie ID mapped to a movie title. It's stripped out here just because of the text length, and then a set of genres. And then there is a total of 58,000 movies that are existing in the movie table. It's actually higher than the number of rated movies, so there are some movies that have never been rated. This is a computation of the data set sparsity we discussed earlier. You can see that sparsity is extremely high. And this is a rendering of a subset of the user movie matrix. So here we're just computing the average rating per movie with the total rating count. Interesting to note that the top three most rated movies, Shawshank Redemption, Forrest Gump, and Pulp Fiction, were all created in 1994. So interesting. I don't know what it suggests about 1994 as a year, but that's interesting to see. The other interesting things to see is that there's a bunch, quite a lot actually, of movies with only one rating, which kind of takes us to render the histogram of number of ratings, and we can see that the majority of movies actually have just a few ratings, right? The vast majority. Rendering the same with a logarithmic scale sort of shows the same long tail that we discussed earlier. This rendering shows the histogram of the actual star rating given, and we can see that it sort of resembles a normal distribution with the mean at around 3.2 or so. And lastly, this is a rendering of the relationship between rating and rating count. it's interesting to see the sort of the structure of this, the plot here. It suggests that movies with higher rating tend to be rated more often. It also suggests that extreme ratings, both high and low ratings, tend to have just a few ratings. So that's interesting to note. Hopefully, it gave us some, perspective on the data itself. Now let's go back to our presentation. Cool. So let's continue. Before we start with more complex modeling, it's important to set a baseline. And we'll start with what we call a popularity model baseline. It's a very simple model. Basically, given a movie, we'll predict the user rating for that movie to be the average rating across all other users who rated the movie. As you can observe, this is not really a personalized model, right? There's nothing we learn from the user preferences. We just base the prediction on what other people thought about this movie. But nevertheless, it's a simple model we can apply. It does have the edge case of there are some movies who were not rated at all. So how would we predict those? And we just make a heuristic decision to set this recommendation to a 3, which is the middle point in our scale of 1 to 5 star ratings, just an arbitrary choice. And there's actually code that I wrote that evaluates this model. It's linked in a notebook. I won't go into it here just because of lack of time, but the TLDR is that this model was trained on 22 million samples or ratings, evaluated on 5.5 million, and the model accuracy had a root mean square error of 0.965. So actually, with a very simple approach, we achieved this baseline, which is actually not that bad. It can definitely be better, but intuitively it means that this model is wrong on, more or less a little bit below 1 star rating here and there. Now the big question is, can we do better? And how much can we do better if we apply more advanced techniques? So let's explore that. If you survey the literature, you'll see a lot of different approaches to modeling of recommendation systems. One of the nice papers from a few years ago is about neural collaborative filtering, or NCF in short. And let's explore it as a way to predict star ratings for a movie. You can see the architecture on the slide here. It's actually, I took this out as a screenshot out of the paper. This architecture basically starts at if you look at the lower part, the input layers take the user and item IDs, or movie IDs in our case, and then feeds those into embedding layers that projects the IDs into dense vectors. So take the potentially one hot item coding vectors and projects it into a smaller dense vectors, which basically these dense vectors model the latent representation for these both users and movies. The next step is we actually the architecture takes these two dense vectors, concatenates them together, and then feeds it into an MLP with X layers. We actually tweak and play around with the number of layers and the size of each layer. Each of the layers in this MLP are dense layers with nonlinear activations. And the last layer actually produces a single output value, which is then our predicted score, which we compare against the ground truth. So that's the architecture NCF proposes, and we'll implement that as a step. It's interesting to know that NCF paper actually proposes an additional, more advanced design, NMF, but I won't go into the implementation of NMF here. With the code we'll go through, it's actually pretty simple and straightforward to add the architecture for NMF, and you can take it as an exercise if you're interested to see how it impacts the model accuracy. You'll see pretty nice gains. As the next step, let's explore how we can use PyTorch to actually implement this model and train it. And let's go to that notebook. Okay, hopefully now it will be faster than before. All right. Okay, so hope you can see this notebook in Colab. Again, it will all be linked in the presentation, so you can check it out. and run it yourself. So we'll follow 3 steps. The first one, data preparation. We'll, just like before, download the data, prepare it for training and eval. We continue to actually create the model we just discussed, the NCF model. And then the third part is does model training and evaluation to train our model and check out what kind of accuracy we can get to. So data preparation, actually scroll through that because we already looked into that. It does pretty similar things to what we've seen before. Here we divide our data set into train and test, which we need because we train our model on a subset of the data and we evaluate it on a separate subset that the model didn't see in training. And the split we're applying here is 0.2. So 0.2% goes to the test or eval, and the rest goes to training. And we can see that the output here is we have 22.2 million samples for training and 5.5 million samples for test. Now model authoring. So we'll implement NCF with PyTorch. It's really intuitive. That's a great thing about PyTorch. If you know Python, you know NumPy, it's really easy to get started and use PyTorch to build a lot of models. So we start by importing Torch and torch.nn, and then defining a class, neural collaborative filtering net, that extends PyTorch nn.module. So this is how our model will get all the PyTorch goodies. The init function, the constructor, is taking a bunch of arguments. First one is the user count, the number of unique users in the data set. And we need that value later on in the architecture. We'll see that. Similarly, the movie count. And then there's a bunch of optional values that have a default value, but we can tweak them to customize and play around with the architecture details. The first one is embedding size, the size of the user and movie embedding. It defaults to 32, but if you increase it or reduce it, obviously you are going to impact the how your model train and the model accuracy and other things. And we'll talk about that, whether bigger is better, a bit later on. In a layer, that's a tuple that defines the number of hidden layers or number of layers in the MLP of our architecture and the number of units in each layer. It defaults, as you can see here, to 4 layers, starting with 64 and ending at 8. That was the recommended architecture in the paper. But again, we can tweak it and see how it impacts the model. We have an optional argument for dropout. So if you want to use dropout regularization, we can specify it. It defaults to none, so there's no dropout. We'll see later on how dropout can affect the training. And lastly, the output range. So what's the output range for this model? It defaults to 1 to 5, which is the star rating scale. Again, we can tweak it based on the specific problems. We'll use that to normalize the output of the model. All right, so the init function basically initializes all these different parts of the architecture. So you can see here we're initializing the user embedding with PyTorch's nn.embedding. We do the same for the movie embedding. Then we initialize the MLP with an internal function within our model to generate the MLP layer. We'll take a look into that a bit later on. And if the initializer argument included dropout rate, we'll also add a layer for dropout. This part is normalizing the output. Pretty simple. I won't talk too much about that. And then the last step is init param, which actually initializes the weights. We'll take a look into that in a minute. That's also a function that is within this module. The generate MLP function we discussed earlier, which generates the internal MLP of the model, is pretty simple. It basically loops onto all the numbers in the tuple that define the number of layers and the init on each layer that was provided to the initialize function. And then it just creates a linear layer, right, with mapping input units to the output, adds a ReLU layer on top of that with nn.ReLU. And then if dropout was defined, it also adds a dropout layer. So that's and then it repeats to build all layers in the MLP except the last one. The last one is created here. The difference is that it's using sigmoid rather than ReLU because we want a range of 0 to 1 at the end of the model. And then actually it's put all of these layers within an NN PyTorch NN.sequential, which is housing all these sequential layers. That's it, pretty simple. Init param method we discussed earlier just initializes the model parameters with Xavier uniform for both the MLP and the embeddings. And lastly, we implement the forward method, which is what PyTorch will call when you do a feed forward, when you do a prediction. It takes two arguments, user ID and movie ID. Those are the inputs for our prediction, and it's expected to return the predicted star rating. Now, this is basically just the flow of inputs through our, this is just the flow of inputs to our network. So we start by actually taking the user ID and taking it through the user embedding to get the user features. Now, remember how initially the initializer of the network took in the number of users. That's where we use it, so we can hash it through the user hash size. Just in case we get something that is out of the range, we can apply it here. Similarly, for the movie feature, with these two features, we called torch.cat to do concatenation of these two dense vectors into a single dense vector that we then feed through our MLP. And of course, we're also doing dropout if dropout was defined, but then we take that concatenated and dropped out input, feed it through the MLP to get the output of the MLP, which is a single value that is coming out of the sigmoid activation. And then lastly, we normalize that output of the MLP to get it into the relevant range, and then we return that normalized output. That's our prediction. So that's our network. That's the definition of the network with PyTorch. Hope it makes sense. Pretty intuitive and simple. That's again the nice thing about PyTorch. If you know Python, it's NumPy. It's pretty easy to work with. The next cell basically initializes an instance of this network, giving it the user count and the movie count, and then printing out the model architecture. So here you can see the architecture we just defined. Starts with user embedding, movie embedding, and then the sequential multi-layer perceptron with a set of linear layers, ReLU, and then the last one is sigmoid. And you can see that the number of units is specified here. This model has a total of 10 million parameters, which translates into a model size of around 41 megabytes. So, it's nice and small model, not too large. Let's see how it does on this data set. Later in this notebook, there's actually code that is actually doing the training and the evaluation and prints out the training curve. I won't go into it here just because of lack of time, but you are free to run this notebook if you're interested and explore the code, etc. I ran it for you, so we can just skip ahead to the results. Okay, so let's go back to our presentation. Okay. All right, so we went through an implementation of NCF, and I actually went ahead and trained the model, and I've trained it on the data set we had with the split we reviewed earlier. So a total of 27 million examples, 80% of them go to training, the rest to validation. The architecture is the one recommended at the paper, 32 embedding size per feature, 4 dense layers, ReLU activation. I used Adam optimizer with an MSC, mean squared error, loss function. I chose hyperparameters, tweaked them around just a little bit. And let's see what results we got. So the results show root mean squared errors of 0.821, which is actually 15% better than our popularity model baseline. Not bad. Training this model on GPU took around 10 minutes, if I recall correctly. So, not as fast as the popularity model, which computes in, like definitely under a minute, but still not that bad, and the results are significantly better. Interesting to look at the learning curve here, and then observe that the model is likely to overfit from epoch 3 or 4. So if you look at the curve, the blue curve represents the training loss, the orange curve represents the test loss. So you can see that while the train loss gradually gets better and better, the test loss actually after the third or maybe fourth epoch already starts actually getting worse, which suggests that our model is actually learning the noise rather than the actual signal. And this kind of shows that there is room to do better and there is room to improve. How can we improve further? There's a bunch of things we can do. Actually, there's a lot of options. We can look at three major dimensions. One is data, the other one is model, and third, algorithm. On the data side, we can try more data. We can try better data. We can curate our data better. We can filter something that may not be useful for our model. Or we can add additional features if our data set has them. And actually, this specific data set does have more information, like timestamp and like genres. We can also tweak the model itself. We can use regularization that we discussed earlier. We can increase the model capacity to make it bigger. We can tweak the architecture. And lastly, on the algorithm side, we can optimize the hyperparameters like the learning rate. We can do learning rate scheduling. We can try different optimizers that may be working better for this use case. We can look into variations of the initialization. There's a bunch of things we can do. The list is very long. In this talk, we won't have time to go over everything. It won't be an extensive review, but I do want to show that how with a few simple tweaks, we can actually get much better results. Let's start with more data. So as we discussed earlier, our NCF model baseline is probably overfitting. We can see the curves. We can see how at some point the training loss gets better, but the eval loss gets worse, which suggests, the model is overfitting. More data may be able to help. So let's take a look at this. In the chart here, you can see the same model tested with different amounts of data. And we can see that there seems to be a relationship between the amount of data, the accuracy the model is getting to. And actually, by taking the same architecture, increasing the examples by just 14%, we get a 0.6% improvement compared to the baseline NCF model, which is nice. So clearly, in this case, less data is more data. Let's look into another approach of increasing the model capacity. So intuitively, by increasing the model capacity, we'll be able to learn more complex representations of users and movies, and also be able to learn more complex relationships between the features of the data. The ways we can increase the model capacity, there are some simple approaches with this specific architecture, like we can increase the embedding size, go from 32 to 64, even 128. We can increase the number of layers, so the model becomes deeper. We can also increase the number of units in each layer, so it also becomes denser. Or we can even introduce new interactions between features, which is actually what the more advanced architecture in the NCF paper suggests. The downside of doing these things is that, first of all, with just sheer increased model capacity with no other changes, we're probably increasing the chances our model will overfit or making it overfit more easily. We'll also be increasing the training time, and with it, the cost of training in terms of hardware and also just the people effort, because when you need to wait for longer times for a model to train as a developer, as a data scientist, it also impacts your productivity and the cost of yourself. And lastly, also bigger model also has impact in the online system we discussed earlier, where inference becomes more expensive, latency becomes higher, etc. So this is something to think carefully about before you do. Some results of tweaking this model specifically shows that, yes, the model becomes bigger, definitely the accuracy improves. However, it seems to have diminishing returns, right, at some point. So this chart here shows 4 different model sizes. And and definitely the biggest one, where we have 5 layers and embedding size is 128, does yield the best accuracy, 0.816, which is just like before, 0.6% improvement versus the baseline. This model was not trained with more data, although the results are similar to previous results of training with more data. It's just a sheer increase of the model complexity. And we can see that this is another approach, effective approach to improve the model accuracy. So in this case, bigger is better, or at least sometimes it is better. And now let's take a look at regularization. So we discussed our model overfitting earlier, and one way to help with overfitting is to introduce regularization. Dropout is one useful technique that was introduced in a 2014 paper by, I believe it was Jeffrey Hinton's team in University of Toronto. And the image diagram here actually is taken out of that paper. It illustrates what dropout actually does. On the left, it's a neural net with 2 hidden layers. On the right, it's an example of a thin net produced by applying dropout to the network on the left. And you can see the crossed units. Those are the ones that have been dropped. We can also observe that effectively this helps regularize the training process, but it also reduces the complexity of the model. That's important to note. Now, using dropout in PyTorch is very simple. You add a dropout layer in your init function of your model. Just PyTorch's nn.dropout, specifying the probability of dropping every unit. You invoke this layer in your forward method of the model, and that's it. Now, one very important thing to note is don't forget to call net.eval when you're evaluating your model, because at a test or eval time, you don't want dropout to be applied, right? You want the full model to run, not a thin down version. Similarly, when you are back to training, you want to call net.train to make sure that dropout is applied, is back applied. So that's an important thing to note. It's often missed. Just make sure you do it. So let's look at the results. Now, actually, if you look at the 2 charts on the right, the upper one shows the training curve with no regularization, just like what we've seen before. You can see that there is overfitting, and this training curve looks really bad. The one on the lower side actually shows the training curve with dropout regularization. You can see these curves are much healthier, right? You can see that train goes down, but eval is also going down nicely. It doesn't seem to overfit. However, if you look at the y-axis, you will note that the no regularization eval loss is actually higher than the one with dropout. Now, what happened here is that dropout effectively reduced the size and complexity of our network, and because our base NCF network is not as deep, not as big, basically it converged to worse accuracy because the model didn't have enough complexity. It's likely that if we use a higher complexity model, then dropout will actually help achieve better results. And indeed, when I ran this regularized model on a more complex architecture, so the bigger one with 128 embedding size and 5 layers, it's actually achieved a pretty good results with really nice learning curves. The model accuracy reached 0.8097, which is 1% better than the same big model with no dropout, and 1.4% better than the NCF baseline. So these are really good results, and shows how we can use regularization and dropout to improve the model accuracy. Now, when we put all of this together, we looked into a bunch of improvements that are independent of one another, and I actually put all of these together. So I combined increasing the number of examples with increasing the model complexity with adding dropout regularization. Then the results are actually pretty good. We achieved a root mean square error of 0.804. That's 2.1% better than the NCF baseline and 16.7% better than the popularity model. Now, 2.1% may seem like something small, But remember that if this improvement is applied to a large-scale production system for a large service, 2.1% is actually huge. It can mean tens or hundreds of millions of dollars for some systems and some customers, or maybe even more. So that's a nice example of an improvement. Now, it's important to note also that these improvements come at a cost. Model size grew 4x. Training time actually grew 24x. From 10 minutes training, we went to 4 hours. And similarly, the training cost rose. So, that's the cost, I guess, of improvements in this case. But that's something to keep in mind. There are additional opportunities for optimizations that we didn't cover in this talk because of the lack of time, but something you may want to explore or consider or think about across both data, model, and algorithm. But taking a step back, I want to do a quick reality check. So how does this sort of example we just went through, how does it relate to what's going on in large-scale production systems and key industry use cases? Actually, industry use cases require much larger scale, like a few orders of magnitude larger scale. If you look at the number of examples for key industry use cases, we're talking not about millions of examples, but trillions of examples. Users from hundreds of thousands to millions or even billions for some services. Items, the catalog of some companies has millions of items, not tens of thousands. And of course, there's also many more features to learn from. So industry, same principles, but much larger scale. And the way in the industry we handle these large-scale challenges is to really investing a lot in the infrastructure. The infrastructure is really key. Having high-capacity hardware, being able to have the software stack that is able to keep up with this high-capacity hardware, having very efficient and reliable distributed training mechanisms with model parallelism that allows us to train on tens or hundreds of machines, and also implement various optimizations for this training phase. And of course, efficient serving, which is key. Applying techniques like model compression, acceleration, and other optimization techniques is key to be able to serve these models at scale. Now, with all that said, the principles we just discussed here are actually very similar or even almost the same. So this has been, I think, a really valid and relevant example if you're interested in this domain. All right, so we reached the end of our talk. Thank you for staying tuned throughout this talk. I hope this, you learned something new, or you sort of got something new to think about, or just, maybe had some interesting examples to consider. I'd love to hear from you to get your feedback, your thoughts, your suggestions. My LinkedIn profile is linked here. I'd love if you would connect with me, let me know what you thought about the talk. And lastly, I want to call out that Facebook is doing incredible things in the field of machine learning and AI. And we're hiring for lots of very interesting machine learning roles. On both the machine learning modeling side and infrastructure side, there's a lot of very interesting and exciting work going on. If you're interested in exploring, reach out to me. I'd love to sort of help you, get you connected, and potentially be able to work together with you. All right. Do we have time for some Q&A?
Yeah, okay. Thank you so much for the great talk.
Happy to.
Yeah, so some of the sessions have already begun, but we can ask some of the attendees if they have any questions. Let's see. I'm just going to go through the chat to see if there's any questions. Yeah, so I would, we'll just give it a sec to see if there's any questions that come in here. All right, so it looks like we don't have any questions, but I just want to.
I'm off the hook.
Thank you once again for the great talk, and we will be sharing the videos with you as well as the attendees as well. So thank you so much.
Awesome.
Thank you.
Thanks for having me. Bye-bye.